Let's now discuss the law of mass action, which relates the free energy change for a chemical reaction, and in particular the standard molar change in free energy, delta G circle sub m sub reaction, to the equilibrium constant Kc. The magnitude of Kc can actually be calculated from the free energies of formation for the reactants and products. From Hess's law, we know that we can calculate the standard free energy change of reaction from the free energies of formation for the products and reactants. And the basic idea, as we've seen for enthalpy, entropy, and free energy now, is products minus reactants, respecting stoichiometry in both of these sums. What the law of mass action does is two things. It defines the form of the equilibrium expression as products over reactants, and it shows how K is related to the free energy change of reaction. What the law of mass action proves, essentially, is that this equilibrium expression is equal to this expression involving the change in free energy for the reaction. Since these two are equal to one another, they are collectively equal to a constant, which we call Kc. We won't prove this here, but it will be proven in a supplemental video. exp here is the exponential function, e to the x power. Think about what happens as the sign of delta G changes to the value of Kc. If delta G is negative, that means x in the argument of e to the x is greater than 0, which means that Kc is going to be greater than 1. Favored products. Remember, we saw before that large Kc means the products were favored. Here, plugging in a negative value here leads to e to a positive power, which gives a Kc value greater than 1. Positive delta G, on the other hand, means that the reactants are favored since the argument of the exponential becomes negative, and Kc consequently becomes less than 1. This is an important intuition to develop. Delta G greater than 0 means reactants are favored, while delta G less than 0 for a reaction means that products are favored. And I should be careful and clarify that I'm talking about standard molar free energy changes of reaction and their relation to the equilibrium constant Kc. We can actually do algebra with equilibrium constants. And this is, on a deeper level, a consequence of Hess's law. If delta G's are additive when, for example, we're summing reactions, we add up two reactions and we can add up their delta G values, then based on the law of mass action, and in particular this equation in the bottom left, how the delta G's are related to the Kc's, if we're adding delta G's inside an exponential, what we're doing is multiplying the Kc values on the left-hand side, right? That is, if the delta G's are additive, which they are, according to Hess's law, then the K's must be multiplicative. That is, if we add two reactions, the Kc value of the summed reaction will be the product of the two. Here are the general rules for determining K when we're adding, subtracting, and reversing reactions. As we just discussed, K for the sum of two reactions is equal to the product of their individual K values. That should also make sense given the nature of the equilibrium expression. If we're going to add, for example, new reactants and new products into this reaction, then we're going to have to multiply by the products on top and multiply by the reactants on bottom when we do this. K for the difference of two reactions is then naturally equal to the quotient of their individual K's, and K for a reverse reaction is the reciprocal of K for the forward reaction. When we reverse a reaction, or even in a sense when we subtract one reaction from another, what we're doing is exchanging the positions of the reactants and products, and all that's going to do to the equilibrium expression is change the positions of the reactant and product concentrations. Put the former reactant concentrations up in the numerator and the former product concentrations in the denominator. Finally, let's take a microscopic look at chemical equilibrium to drive a few conceptual points home about what's happening in an equilibrium system on the molecular level. So in this simulation environment, we have two sort of chambers separated by a kind of wall, this yellow wall that you see in the middle. The vertical axis here is actually meant to be free energy. So we can change the relative free energies of the reactants and products and thereby change delta G for the reaction. The standard free energy change you can think of as the difference between these two sort of bins for the reactants and products. I'm going to lower this wall down initially to take off the table the issue of activation energy and the idea that the molecules may need some energy to convert from one side to the other. But watch what happens if I add, for example, 100 particles into this chamber. Everything starts off as A, and that's a non-equilibrium state initially, and so on the whole we get molecules moving towards B. Over time, more and more molecules move towards B until we reach a state eventually where the number of molecules of A and the number of molecules of B in a bulk sense aren't changing. You can see we're still getting microscopic changes in the numbers of A and B, but eventually these values will stabilize and we'll get some quantity of molecules on the A side and some quantity of molecules on the B side. Because B's free energy is much, much lower than A's, we have a much larger concentration of B in the equilibrium state than A. But watch what happens when I equalize the levels of B and A and allow the system to come to equilibrium again. Now the two free energies are equal, and I'm going to lower down the activation barrier again. Watch what happens to the numbers of A and B particles in the equilibrium state. The sizes of the letters, by the way, give you a sense of the relative concentrations of the two. There are some fluctuations, but for the most part these are small fluctuations about the 50-50 mark. With the molar free energies of the reactants and products equal, we have a 50-50 mixture of reactants and products at equilibrium. And even though on the macroscopic level it appears that the numbers of each type of particle aren't changing very much, we can see there's still a lot going on the microscopic level. Forward and reverse reactions are still always occurring. What's not changing, or changing with only very small fluctuations, are the numbers of molecules on the reactant and product side. For every green molecule that goes over to the right and becomes red, there's a red molecule coming back to the left and becoming green. That is to say, the rates of the forward reaction A to B and the reverse reaction B to A are equal in this equilibrium state. It's only a 50-50 mixture like this when the free energies are equal. If I, for example, raise the free energy of B, and it's going to make me raise the activation barrier to do this, but if I raise the free energy of B quite a bit, the resulting equilibrium state has mostly A and a relatively small amount of B. Even so, there are still particles of A becoming B and particles of B becoming A, even in the equilibrium state. Microscopic change is still occurring in the equilibrium state.